Okay, this is 5.3. Graphs of rational functions of the form f of x equals ax plus b over cx plus d. So we've already started to look at this in the last two sections. I want to just go back and refresh everyone's memory of the summary of 5.2. Okay, because it was a long lesson. Again, it actually was it was just an investigate, and there wasn't many examples to do, but there was a lot that we went through. Okay, so just as a reminder, when we have a quotient function like this, p over q, and we end up with a 0 over 0, that represents a hole in the graph. When we end up with a number over 0, we get a vertical asymptote. Okay, these are the key things we learned last time. And then when we found out when we have a rational function p over q, when the degree of p is less than or equal to the degree of q. So when the numerator is less or equal to the denominator, that's the degree, we have a horizontal asymptote at the division of the coefficients. Okay, so if the degree is equal, here's the example, we have an horizontal asymptote at 2 here. When the denominator has a greater degree, so this is the one thing that's missing out of this summary, is when the denominator has a greater degree, we have a horizontal asymptote at y equals 0. Okay, we'll show that in this example here. And finally, when we have a rational function where the numerator has a greater degree by 1 over the denominator, we have an oblique asymptote. Okay, so denominator greater degree, we have a horizontal asymptote. When they have the same degree or more, we can have a horizontal asymptote at the division of the coefficients. Any questions about that so far? Okay. All right, 5.3. So our goal is to sketch graphs of rational functions. The radius in centimeters of a circular juice blot on a piece of paper towel is modeled by this, where t is measured in seconds. According to this model, the maximum size of the blot is determined by the location of the horizontal asymptote. Okay, so we're very applicable examples here. Juice blots now. So we had our Jennifer's homework question. Now we have stains on a piece of paper. But anyways, it's getting rather complex, so I guess they're running out of kind of practical examples. So how can you find the equation of the horizontal asymptote of the rational function of this? Okay. So without using graphing, determine the domain, intercepts, vertical asymptote, and positive negative intervals of the simple rational function. So it's important now, guys, that you're not going to have a graphing calculator when you write these tests. Right? So we have to be able to do a lot of these things algebraically, okay, and kind of understand what's going on the graph, but understand how that also corresponds algebraically, okay? So let's see if we can go through this. So determine the domain. So what would be the domain of this? So your instinct, I think, which my instinct is, would be to try and graph it first, right, to get the domain, because then you could visualize it a lot better. Okay, but how could we find the domain without graphing? Let me ask it another way. What do we know for certain cannot be in the domain? What do we know? Which point or x value definitely not in the domain? Lyndon? The x-intercept could be in the domain, should be in the domain, yeah. So not that, yeah, Alan? Negative 1, right. Why negative 1? Right, so x cannot equal negative 1. Okay, and the reason why is because if x is negative 1, we're going to have a number over 0. And what is a number over 0, which we just reviewed? Right, it's a vertical asymptote. So x equals negative 1. So at okay, because at x equals negative 1, we have a number over 0, which is a vertical asymptote. Okay, and therefore, because we know this is a polynomial function, we have all whole number exponents. We know that this graph is going to extend in either direction. Okay, and we know it can't be -1, so our domain then is going to be Any questions about the domain? Okay, another way to write that domain is you could write it in interval notation. Okay, that's a -1, sorry. So I hope you can follow that notation as well. It's just everything on the left-hand side up to -1, but not including -1, and then everything after -1. But again, open brackets, signaling not including, okay? So that's our domain. Our intercepts now. So how are we going to find our intercepts? How do we find the intercepts? Nailed? How do you find intercepts? What do we do? Yeah, x and y intercepts. How do we find them? So how do you find the x-intercept? One as y? Why 1?
Wait. Never mind. Sorry.
Marco in the back, x-intercepts? How do you find x-intercept?
Y equals 0.
Right. So we say y equals 0. So we're going to plug in y equals 0 for our function. So 0 is equal to x plus 1. Therefore, x is equal to 0. These cancel, right? Everyone understands that? If I multiply both sides of this equality by x plus 1, the x plus 1's cancel, and I'm left with x equals 0. Okay, so our x-intercept is at x equals 0. Now our y-intercept, Luigi.
It's when x equals 0.
Right. So I'm going to plug in x equals 0 to the function, and I get, which is 0. So y is equal to 0. Okay, 0 over any number is still 0. Any questions with the intercepts? Okay, so we haven't graphed anything yet, which is a good thing, right? Because we want to develop all these rules, and then our graph will be a lot easier to create. Okay, vertical asymptote. We already talked about this. Where's the vertical asymptote? Philip. Right, vertical asymptote at x equals -1, and why? Because that gives us a number over 0. Okay. And the last one, positive and negative intervals of the simple rational function. This is one of the harder ones to come up with without a graph. So the concept is simple, right? The concept is when are the x values positive and when are they negative? But it's not as easy to figure that out algebraically. It's easy if you graph it, then we can just look at it, right? But to figure that out algebraically, there's no simple kind of equality that we can create and then solve for. Okay, so we have to use the other information that we know to figure that out. Okay, so the way we do that the way we do it is to make a table, okay? And you've seen this in the last section. We did this briefly. I showed this where we put the ranges on top, and then we put the numerator and the denominator on the side, and then we actually put the result here. Okay? So anybody know why I put in these values? Remember, I don't have a graph to work with yet, right? So somehow I came up with these intervals. Anybody tell me how or why? Yeah, right here.
They're the x and y intercepts.
Right, there's the x and y intercepts, which is 0. Remember, these are all x values. Okay, so don't get confused about that. These are ranges, or sorry, domain values. Domain values. X range, kind of. Okay, and the reason why is because negative 1, yeah, Philip?
Why is it -1 to 0?
Right, no, that's a good question. That's what we're talking about right now. That's exactly what I'm trying to ask and have you guys figure out. Okay? The reason why we know it's negative infinity to negative 1 is because negative 1, we know there's a hole there in the graph. There's a vertical asymptote. Okay? So without graphing it, we still recognize that negative 1, you know, the graph is not passing. It gets to negative 1 and it's got a curve, you know, either up or down. Okay? So something funky is happening at negative 1. The reason why we put in 0 here as a key point is because 0 is our x-intercept. So that's when we actually cross the x-axis. So if we're talking about positive and negative intervals, that's a really important point for us, right? Because that's where we're actually crossing over. So that's why we need to consider negative 1 and 0 as our ranges to find out where the positive and negative intervals are. Does that make sense? Any questions about that? So now we can sub in a value for x. This is going to be negative, any value for x. If x is less than negative 1, this is also going to be negative. So our result is positive. Okay? This case between negative 1 and 0, this is going to be negative, this is going to be positive. When we divide a negative by a positive, we get negative. And finally, this is positive, this is positive, this will be positive. All right? So therefore, our positive interval is from negative infinity to negative 1 and from 0 to infinity. And our negative interval Any questions about that so far? Okay. So that's it for part A. It's a simple rational, so negative intervals. So yes, it's a lot, but we have a lot of information now about the graph. That's the point. Next, B, copy the following table and complete them by evaluating f at x for each value of x. Examine the end behavior by observing the trend in f at x as x grows positively larger and negatively large. What value does f at x seem to approach? Okay, so we're trying to determine here the end behaviors. Okay, so we all know how to do this, right? We take 10 and we sub it in for x, and we get these values. Okay, so if you work them out, you get these two values. Okay, so what that's telling us then, as x is approaching infinity, the value of y is going closer and closer to 1. Okay, so think about that now on a graph. So x is going, you know, closer and closer, farther and farther to the right. The y value is getting closer and closer to 1. When we go far, far to the left, the y value is coming down from above 1. It's going closer and closer to 1. So what does that tell you? What's happening at 1? Yeah.
Horizontal asymptote.
Right. So there's a horizontal asymptote at y equals 1. Okay? And we should have known that, actually, from the last section. We knew if the degree is the same in the numerator and the denominator, you divide the coefficients and you have the horizontal asymptote. Okay? So this is just a proof to what we already know, that there's a horizontal asymptote here at y equals 1. Okay, and that's from dividing the coefficients, 1 over 1. Any questions about that? Okay, so we have a lot of information now about this graph. That's the idea. We haven't used the graphing calculator. We've just used, all of the rules that we've learned. So we should be able to get a pretty good graph now. So it says, write an equation for the horizontal asymptote for the function in part b, y is equal to 1. We just talked about that. Repeat a, b, and c for the functions. Okay, we're not going to do that for now, but let's do a little bit of it. We won't do them fully, but here we know that there's a horizontal asymptote at what? At y is equal to 4. Okay, there's a vertical asymptote at x equals -1. Anything else we know right away? Okay, we know our domain cannot equal -1. Okay, that's that same condition as the last problem. And we can figure out our x and y intercepts pretty easily, right? So our x-intercept, we're going to set y equal to 0, and we get x is equal to 0. So our x-intercept, x is equal to 0. Y-intercept, we set x equal to 0, and we have y is equal to 0. Alright, so the only one that really takes a long time is the positive and negative intervals. You have to set up that table. Okay, and you use the x and y, the x-intercept as well as the vertical asymptote x values to determine your ranges. Okay, so if we were to do this one here, we could say that there is a horizontal asymptote at, Gennaro? Where's the horizontal asymptote for this one?
For x plus 20? No, I think for which question?
For this function, what's the horizontal asymptote?
2 over 3.
Right. Y equal 2 over 3. And Gianluca, there's a vertical asymptote for this. Where would that be? Yeah, good. So you're going to set the denominator equal to 0. Okay, because that's when we have horizontal asymptotes, and then you're going to solve for it. Any questions there? Okay, then we could find our x-intercepts. So your x-intercept is when y equals 0, it's x equals 0. And then our y-intercept, x is 0. This one, Nicholas, our horizontal asymptote.
Horizontal asymptote?
Yeah. You understand that? Why?
Yeah.
Okay. Our vertical asymptote. David? Our x-intercept. Daniel?
2 over 5.
X-intercept, so y is going to be equal to 0.
Yeah, oh.
So I got to review this. So 3x minus 2 over 2x minus 5 is equal to 0. Right? Because we want to get the y-intercept. No, the x-intercept. Yeah, equals 0. So this cancels. So you have 3x equal minus 2 equals 0. 3x equals 2. X is equal to 2 over 3. Okay? Nailed y-intercept?
Good.
Not hard, right? We're just subbing in value of 0 for x. You get negative 2 over negative 5. The negatives cancel. 2 over 5. Any questions there? The last one is the positive and negative ranges. Remember, the way you do that is you set up a table with the numerator and the denominator, and then you use these values as your range values, starting from negative infinity and going to positive infinity. Okay? So if I were to set up this one, just as an example, you would put 3x minus 2, 2x minus 5, and our ranges would go from negative infinity to what? What would be my first point? Yeah, Lyndon? Negative 2? Did you say negative 2? Why? No. It's going to be the smallest value here, right? So not this one, not this one. It's going to be 2 over 5. Oh wait, sorry. 2 over 5 is a y-intercept. We don't consider this one. So it would be 2 over 3. Does that make sense to you guys? Is there any questions about that? The next interval then would be 2 over 3 to what? Okay, and then you determine this is positive, negative, and then the result. That will tell you where the graph lies, above or below the axis, okay? Any other questions with that? That's the trickiest one without a graph to figure out. You got to make a table, put your numerator and denominator on the left side, and then put your ranges on the top. Your ranges are dictated by your vertical asymptotes and your x-intercepts. Okay? Okay, next one. Verify your results by graphing, noting similarities. Okay, fine. Make a list of equations of the functions and the equations of their horizontal asymptotes. Discuss how the degree of the numerator compares with the degree of the denominator. Explain how the leading coefficients of x. So this is from 5.2, right? We already made that conclusion. So it's just a review. So we know if the numerator and the denominator have the same degree, you need to divide the coefficients to find out where the horizontal asymptote is.
Would you find that without using the way that you taught us?
You wouldn't use the way that I taught you.
So why would it say to figure out an app to do it?
Where?
You just said you learned that already in the previous section.
Yeah, so it's just, okay, let's read. So it says make a list of the equation of the functions, the equation of their horizontal. It's just asking you, how you figure it out. Sorry. It was this table, right?
Oh, okay.
Right? That's how we figured it out where they were.
Oh,
Okay?
okay.
So it's saying, like, once we do this table for all of these functions, what do you notice? And we notice that rule that we developed in 5.2. Okay? All right, let's go on to the first example. Determine how the graph approaches its vertical asymptotes. All right, so the first part would be to find out where the vertical asymptote is. So who can tell me that? Elijah, where's the vertical asymptote for this? Yeah, -2, right. And Elijah, why is -2 a vertical asymptote but not a hole?
It's not a hole because what's called the numerator doesn't have a greater degree than the denominator.
No. No. Damn.
Because if you put in -2 on the x at the top as well, it won't be 0/0.
Excellent. You got that, Elijah? So it's because it's a vertical asymptote at x equals -2. Why? Because it's a number value over 0 when x is equal to -2. Okay, that's why. If we had a 0/0, it would be a hole. Okay? All right. So, one way to do it, to find out what's happening on either side, or this is the only way we know so far, is to figure out, what are the values just to the left of the vertical asymptote, and what are the values just to the right of the vertical asymptote. If we can figure that out, like if the value is really positive, it's a high positive number, we know that the curve is turning up, right? Does that make sense? So if we have our graph here, and we have x is equal to -2 here, one way to figure out what's going on here, what's happening with the graph, is to plug in this point here. So we plug in -1.9, and we plug in this point here, -2.1, and we can see either the value of y is up here, or it's down here, up here, or down here, and then we can determine which way this thing is turning as it approaches. Does that make sense? So that's what we're doing now. We're testing values just on either side of the vertical asymptote. Okay, so that's why they choose -2.1. So they're approaching from the left here. And they figure out, they just plug it into the original function, and they get a really high positive value. So 113. So we know that this is coming up like this from the left-hand side. Okay? So on the left-hand side of the vertical asymptote, the values of the function are positive. So as x approaches -2 from the left, the function f at x goes up. Like that. Okay? Now we check the other side, -1.9, and then we find out it's a very negative number. These don't have to be opposite. Be careful. Don't just check one, because you could come up like this too on the other side. It happens to be opposite, and I think most of the examples you'll do are opposite, but it's not always the case. Okay? So that comes from this. When f is -1.9, y is -107, so it's way down here somewhere. That's why I know that this arrow goes like that. Any questions about that? Okay. On the right side of the vertical asymptote, the values of the function are negative. So as x approaches -2, our approach gets negative. So here's the graph they created. Okay, so same idea. They're going down when approaching from the right, and they're going up when approaching from the left. Okay, and that's all the question asked for. It said, determine how they're approaching. And this was a lot faster than this, right? You don't have to do all this, right? We don't have to plug in all these increasing values. Just plug in a value just to one side of the vertical asymptote and figure out if it's positive or if it's high positive or high negative, okay? Careful though, just keep in mind, and this will probably be for later, but if there's a horizontal asymptote somewhere, that's gonna mess things up too, right? So just be aware of that. And we'll see more examples of that when those scenarios occur, but typically you would see something like that happening. Okay, if there's a horizontal asymptote as well. Okay, example 2. Using key characteristics to sketch the graph of rational functions. So for each, we need to do everything that we were doing in the investigate. All right, so let's do the first one. We'll do it up here. So our domain. Here's the function down here. You can tell me the domain. Anthony?
Is 3 x not equal to 3.
Good. Or another way to write that, again, negative infinity to 3, 3 to positive infinity. Okay. Intercepts. So our x-intercept. Joseph.
The